let's go to page 118, and this is lesson 9.1. This lesson is on drawing the complex numbers. So over here, I give you a couple examples. So for example, if you have like 3 plus 4i, and normally when you're doing the graphing, okay, when you're sketching, normally you deal with x and y, but complex number you're dealing with the real and imaginary. So instead of x and y over here, this would be the real number, and this would be imaginary number. Okay. So this 3 would be the real number, and this would be imaginary number. So to plot this point, you just go 3 in this direction. So go 1, 2, 3, and go 4 in that direction. Okay, and so this point would be 3 plus 4i. So it would be 3 plus 4. Okay, so that would be how you plot the point. You also have another point. It has negative 5 plus I. So in this case, you just go negative 5. 1, 2, 3, 4, 5, and then I. So this point would be negative 5 plus I. And you have another point, negative 2 minus 2i. So you just go negative 2. So it would be right over here. So this would be negative 2 minus 2i. Okay. So just go negative 2, negative 2. Okay. Now I just give the direction. Okay. And it's always going to be the real part and the imaginary part. Okay. So now let's go to page 119. And let's do the exercise 9-2. Exercise 9-2. It says draw the set of points z in a complex plane such that, so you have the 3 parts. Okay, so z is a complex number, so this is going to be equal to x, right? X is a real direction, plus y in the I directions. Okay, so this would be like the form for the complex number. So the first part, it says R e of z. So what it's saying is that the real part of the complex number z equal to 1. So real part of z is this over here. So what it's saying is that x equal to 1. That's what it's saying. So to graph that, you just, in this case, would be just this. Okay. So this would be the imaginary, this would be the real number, and so here would be x equal to 1. Okay. Or the real part of z equal to 1. So you want to be more exact. Okay, so it would be just like x equal to 1. That's all it's saying. Okay. Now when you're doing the part 2, you have imaginary part of z plus the real part of z equal to 1. Okay. So if you look up here, the imaginary part of z is y. Right. So this would be y, and real part of z is x equal to 1. Okay. So that's what this is. And so to graph that, if you don't like it this way, you can switch it so you can have x plus y equal to 1. So when you graph, so this would be the real and imaginary. So you can just plot points. So you're going to get x. So x equal to 0, x equal to 0, then y will equal to 1. And if y equal to 0, x equal to 1. So you're going to get. So you're going to be looks like this. Okay. Okay, then if you go to the third part, you have the imaginary part of z is less than 1. Well, imaginary part of z is a y. So basically what you have is y is less than 1. So when you graph that, you're going to have this right over here. So y equal to 1 will give you, and there's no equality, so it would be dashed line, right? And it's less than, so it would be this over here. Okay? So it's not too bad. Okay, now, after that, so let's go look at the exercise 9-2. Okay, it says for z equal to 3 plus 2i. It says draw, you want to draw z, and then you want to draw. So when you have a bar on top, that's your conjugate. Okay, you got z squared. Okay, and z minus 1. Okay. So z, you just go 1, 2, 3, and 1, 2, right? So that's this part, right? So very simple. So that is this over here. Now, when you have a bar on top, that's a conjugate. So z conjugate equal to 3 minus 2i. Okay? So when you graph, you're just going to go 1, 2, 3, 1, 2, right? So that would be your 3 minus 2i. And z squared, you just go ahead and multiply that together, right? So you got 3 plus 2i squared. So you're going to get 9 plus the middle term will give you 12i, and the last one would be plus 4. I squared would be minus over here. So this will equal to 5 plus 12i. Okay, again, so when you sketch that, just go 1, 2, 3, 4, 5, and then you got 1, 2, 3, 4, 5, all the way up there, somewhere up there. Okay, and that would be it. And z minus 1, so you just minus 1, so z minus 1 will equal to 2 plus 2i, right? And then you just go and sketch that, so it'll be 1, 2, 1, 2, and that's it. Okay? Okay. Now, next part is, next part we're going to do is going to learn how to convert from rectangular coordinates into polar coordinates. Okay. And so, on page 119, you have the x equal to r cosine theta. Again, think about the circle, right? You know, the polar coordinate, you have a circle. And so if you just have something like this, so this is r, and this is theta, right? So the vertical would be r sine theta, and horizontal part would be r cosine theta, right? And so that's where it came from. Like x is the horizontal part, so it'd be r cosine theta, and y would be equal to r sine theta. So you can already just basic the trigonometry. And r, if you use Pythagorean theorem, r equal to square root of x squared plus y squared, right? So x squared plus y squared equal to r squared, and you take the square root, right? And tangent theta, I don't like the way the book uses r10. I'd rather to keep it in the tangent form. Okay, so tangent theta equal to the vertical over horizontal, so it'd be equal to r sine theta, right? That's y over r cosine theta. Okay, and so you can, and it also equal to y over x. Okay, depends on what it's giving. Okay, and by the way, what is y over x? This is equal to the slope, right? So tangent theta equal to slope, right? Y over x, that's your slope. Okay, so those are kind of all the connection between them. Okay, and also r cosine theta, this is equal to the real part of z, right? And this is equal to the imaginary part of z. Okay, so kind of how to make the connection, the relationship between all of them. Okay, so now from here, you can see that z equal to r cosine theta, the real part, plus I r sine theta. Okay, so again, r equal to z equal to r cosine theta plus I is a direction, right? And over here, right? So that's why it's equal to. Okay, now instead of writing all these, usually they kind of use a shorthand. So this is z will equal to r, and it would be cis theta. So c came from cosine, I sine. So cosine I sine theta. Okay, so that's how they write it in this form. So you're going to see this a lot. You're going to see this a lot. Depends on what book you use. Also, another way to write this would be r e to the I theta. Okay. Okay, so this is another way of writing it. Most of the college book use this form. Most of the high school textbook use this form. So if you compare a math meet, for example, you're going to see this form or this form. Most likely would be this form. Okay? But they are all the same. Different way of writing it. Depends on what book you're using. Okay. Okay. So let's go ahead and do some examples. So let's go to page 119 and let's look at example 9-1. It says find the polar representation of I. Okay. So again, if you think about the circle, right? So this I means in this direction. This is I. This is R, right? So this is one I, right? So this is going to be right over here. So that's your rectangular coordinates. Now, if you think about if you superimpose the circles on top of it, this will equal to 1. Okay, the length is 1, so the radius is 1, and this would be CIS of 90 degrees, right? So that's what equal to. If you put a coordinate form, this point would be, the radius would be 1. Now remember, the polar form is r theta, right? So this would be 90 degrees, okay? So again, there are so many different ways you can write this, and if you use the radian, then it would be 1 comma pi over 2. Okay? And if you write this in the exponential form, this would be equal to e to the I 90 degrees. Okay? So again, over here is 1, right? So 1, and now there's an advantage of each system. Okay? Again, there's an advantage and disadvantage of each system. Depends on what you have, depends on what you're going to do with it. Sometimes one way is easier to use than the other. Okay, so you kind of have to be comfortable with each one. Okay, okay, and let's go to exercise 9-4. It's sort of point you have a. So the point r equal to 2, theta equal to pi over 3. So basically you have 2 comma pi over 3. And also you want to do the 3 comma pi. Okay, so to draw that. Now whenever you're doing the polar coordinate, okay, it's easier. I find it's easier to do the angle first than the radius. Okay? So pi over 3, that is like over here at 1 o'clock position. And now remember the polar graph has a circle going like this, right? Okay. Then after that, after you get your angle, then get your radius. So radius 2, so it'd be from here you go 1, 2, and so it'd be right over here. Okay. Now on this one over here, so this one is over here. Now 3 pi, the pi would be on this direction, and the 3 would be right over here. So this would be 3 comma pi over here. Okay. So again, it's easier to do the angle and then do the radius. No? Yeah. Okay, let's do exercise 9-5. So exercise 9-5 is a sort of curve r equal to 1 and theta equal to pi over 3 on a complex plane. Okay. Okay, so r equal to 1, the radius of 1 is like this, right? And pi over 3 is this. Okay, so you got pi over 3 and r equal to 1. Actually, I think this is 2 different problems. Okay, so r equal to 1 would be like this. So if you do it in a complex plane, this would be a circle with radius 1 and center is 0, 0. So this would be x squared plus y squared equal to 1. Right? Now this one over here, so theta equal to pi over 3, so that's your 60 degrees, right? So if you just draw any point down, this would be equal to 1, 2 square root of 3, right? So in this case, the slope equal to square root of 3, right? Right, slope equal to y over x. So basically, you have y equal to square root of 3x, right? The slope intercept form, because it goes to the origin. Okay. So that's how you kind of convert. Okay, so you have to kind of be familiar with all this and know how to convert back and forth, okay, between rectangular and polar. Okay.